From now, we will examine the weight of our points of view, now also acting on the direction of some known forces in space-time. When analyze gravity, you realize that between two bodies of different masses that attract each other, the body of greatest mass is the one which wins and determines the direction of the prevailing force. Potential gravitational energy follows this principle. It is known that if the largest pulls the smallest towards it, the same happens in the opposite direction, although, in the end, the one with the greatest mass prevails. In the case of the gravitational attraction between the Sun and the Earth, the center of gravity would be so close to the star that, for the purpose of calculating the force, the Sun would be placed virtually over the center of a circle. A circle is a kind of ellipse, in which the two foci overlap over the center. The gravitational force that would act on the Earth would have a radial orientation, and the planet would travel in an almost circular orbit. There is nothing wrong with this analysis when it comes to the laws applied to planetary movement. Evidence that the biggest and strongest do not always prevail is embedded in the Big Bang theory. One of the most accepted hypotheses is that the singularity would have originated from a temporal inversion and from the gravitational collapse of a body of very high mass, forming a black hole. Considering, as defended by most astronomers, that the expanding space would behave in the same way as an elastic strip, as the universe expanded and the space stretched, the singularity would have to pull the galaxies towards it, delaying their movement. When the rubber strip of space stretched from the center, the force would point in the opposite direction, or towards the singularity. In the book Physics 2, R. Resnick and D. Halliday, the gravitational potential energy is described following the model of a simple harmonic oscillator. In one of the configurations mentioned, the Earth and the particle would be infinitely distant. We, then, assign zero potential energy to the system. Therefore, the configuration of zero potential energy is also that of zero force. We make a similar choice when defining the zero-energy configuration of a spring as the configuration in which it is at its normal length, not stretched, in which case the restoring force is zero. The negative sign indicates that the potential energy is negative at any finite distance. That is, the potential energy is zero at infinity and decreases with decreasing distance. This corresponds to the fact that the gravitational force exerted by the Earth on the particle is attractive. When it moves from infinity, the work done by this force on the particle is positive. The gravitational force that acts on the particle has a negative sign, indicating an attractive force. That is, a force that pulls the particle towards the Earth. This would have to be valid also for the influence of the singularity on the expanding galaxies, attracting them. Inflationary theories support the opposite, since the redshift tells us that galaxies would be continually moving away from each other as quickly as the more distant they were. The strongest and the most massive, in this case the black hole, represented by the singularity of the Big Bang, would be losing the dispute for a mysterious energy called dark. Edwin Hubble discovered that the other galaxies moved away from the Milky Way in 1929 when he realized that the most distant galaxies moved faster than those closest to us. He understood that could measure their speeds by measuring their wavelengths through a prism. This is called redshift, and is still used to measure distances in space. The potential energy generated from the Big Bang would be negative if the space around the galaxies obeyed the model of a rubber band that stretched. This means that the Big Bang would pull the galaxies towards it, slowing their movement. In relation to the particle attracted by the Earth, you could replace the Earth with the singularity of the Big Bang. The behavior of galaxies would be the same as expected for the particle placed at finite distances. They would be attracted by the uniqueness. When you place the 0 point of time in the position of a star, which could be our Sun, you are assuming that the star would have the unlikely potential to manifest its point of view, so it would be placing itself in the center of what it observes. For his part, when the observer, and not the star, expressed his point of view, he would reverse the direction of the arrow of time, as it would no longer point to his future, and would now point, continuously, to his past. The same inversion would happen with the direction of the potential gravitational energy. Now, the Earth would also pull the Sun towards it. The same could be predicted when thinking about the singularity of the Big Bang, as these are ideas developed from the observation of events that, in principle, would have to be on the inside of space-time. The following graph shows that, if the post-singularity space assumed the same behavior as an elastic strip, the expansionary movement would be associated with a negative work in that space. The potential elastic energy would be negative at finite distances. That is, the gravitational force would be attractive and it should pull the galaxies towards the singularity. If time existed within the future outcome of the Big Bang, it should contract complementarily with the stretching of space. In order for the observer to remember the singularity and the expansionary movement itself, it would be necessary for the space to contract at some point, which would inevitably be accompanied by an inversion in the direction of the arrow of time, followed by a time dilation. Before this inversion, there would be no measurable movement, but if there were, the galaxies would move away from each other in delayed motion. This is in clear disagreement with the redshift, Doppler. When the cosmic radiation emitted 13.7 billion years ago by the singularity reached the Earth and spread, there would be an apparent inversion of the arrow of time in the position of the isolated observer. He is the only living being that can decode the information and emit his point of view. The arrow would continually point in the direction of his past. At this point, the direction of the potential gravitational energy would be determined by the bodies with the greatest mass. Between the Sun and the Earth, for example, the gravitational force would point to the star. The potential gravitational energy would be negative at finite distances, according to Resnick and Halliday. The spring of space would already appear in its contraction phase, after having been at rest in infinity. Note that there is no longer a stretch phase of the spring within space-time, which represents a problem that is difficult to solve for inflationary theories. The tracking of cosmic radiation emitted by distant galaxies is the only source of information we have, and this radiation is always present in our past or after it spreads on Earth. This remote tracking, based on the redshift, shows the waves as if they were continuous. Thus, light would no longer depend on the direction of its propagation, which prevents us from determining, in isolation, whether the space is currently in its contraction or expansion phase. The attraction between bodies of greater or lesser mass became reciprocal. However, the expansion of the space strip, and not its contraction, is what should promote the attraction of galaxies in the direction of the singularity, and a delay in their movement, as the singularity is the body with the greatest mass possible. In this context, the observer's point of view would be weighing, added by the apparent inversion of the time arrow, in its position. On the other hand, when we track cosmic radiation in the past, the contraction of the elastic strip within space-time would be apparently moving the galaxies away from each other in the presence of accelerated movement. This suggests that the contraction of space in the post-Big Bang is what would be exposing the previous phase of space stretching. Therefore, the expansion would always be evaluated outside of its own time, or as an image of our own past. It is as if the expansionary movement acted temporarily as an information eraser, even if it remained there. I will give an example of the kind of prison that space-time would represent for our consciousness, not for our physical bodies. We usually measure the distances and speeds of the stars through the light emitted or reflected by them. When we do, we take into account that the light has a fixed and limited speed. With that, the light of the star should take time to reach us on Earth. In this procedure, we usually forget that if its light had not yet reached us, the star would not exist, even if it were there. This creates a principle of exclusion from access, since we cannot remember an event that, even though it has already occurred, has not yet provided access to information carried by light. We are forced to conclude, in the case of our visible star, that its light would always have been here. It does not matter, in this case, whether or not it had previously moved in space.